Hello, and welcome to another brief video lesson on photometry, flow of a photometry project. This video lesson assumes you've already reviewed photometry and overview, comparison stars, and the aperture photometry lessons. If not, I suggest you pause this video and review those lessons. In this project, we'll discuss the basic outline of a photometry project from start to finish in order to put it in a global context. I recommend that you just watch this video and listen. Later, you can go back with a PDF and follow the steps and review this video as necessary, but we're going to discuss these in fairly high level right now. The steps. You first want to determine your project type. Are you doing exoplanets, variable stars, asteroids, comets, what have you? What is the goal of your project? You need to locate that target in the sky. One of the things you have to keep in mind if doing asteroids or comets is it moves. So you have to locate the target in the sky on the day that you plan to image, because 3 days later, that asteroid or comet won't be there. It moves. So there's a difference between a moving and a non-moving object. So locate the target in the sky, determine what your target is going to be. If possible, determine what stars and there are not variable and can be used as comparison stars. So back to the Landholt standards, the APAS standards. In this case, in this example right here, I've used a map from the AAVSO that shows you confirmed magnitudes of non-variable stars that could be used as comp stars. Then determine the best time of imaging, for example, air mass. Is it above 30 degrees on the horizon? Is it overhead? When can you view this? It may be possible, given the time of, let's say, an eclipsing binary transit, that you have to view the star much lower in the sky than is ideal. Conditions will sometimes dictate that, and you have to adapt as necessary. You can't always demand that an exoplanet or the eclipsing binary transit will happen straight overhead. Determine the best telescope for imaging. This includes filters to use. How big is the camera? What are the filters available? What do I need for this project? Then schedule your images for acquisition. Some of the image scopes that we have available: Las Cumbres Observatory, Brief San Diego, Brief Texas, or any other telescope you may own. After image acquisition, the image that was acquired has to be processed. So some of the key things you need to do is you need to calibrate this. You need to get the dark subtraction, the flat subtraction, the bias subtraction. Encourage you to review those lessons if you need to. You need to put the RA deck in the image, the WCS coordinates, so that your software will know where it's looking in the sky. Look for cosmic rays, subtract those. Review the images, good images, bad images, something blurry, something out of focus, something didn't work, shutter, what have you. That happens. And then your methods for processing could be the OSS pipeline through Dr. Michael Fitzgerald. You may use an AIJ process. You can process on the BARC computer with Maxim or Mira. Or you may have a platform that's available to you that you would like to use. The post-processing path, other than running images through the OSS pipeline, you need to open all images. If they've been calibrated, then move on to the next step. If they haven't, calibrate them, darks, bias, flats. Place an aperture over that target star. Then locate your comparison stars. If the magnitudes of those are known, such as APAS or Landholt or in the AAVSO chart, that's fantastic. You can insert that information. That will help you with a magnitude differentiation of your target star. If they're unknown, then the resultant plot of the target star variability will be compared to the comp star. But remember, the comp star has to be non-variable. It cannot fluctuate during the time of your images. Calculate the target star flux changes using software. Review the plot from your software package. Is it AIJ? Is it Maxim? Is it Mira? What is it? Perform the period analysis of what you have determined. So for example, if you've received a period here, you can plug this into Paranzo or a tool at AAVSO, and you can help get a determination of what your actual period is you're looking at for the object that you chose. There's an error determination. To determine error measurement, use the differential count of the comp star counts by subtracting the average of all of the comp star counts over the period of time. The root mean square, the RMS, of the differential comp star measurements is an estimate of the errors. Here's your formula. So the root mean square is the sum of all the counts squared. Remember back to our statistics lesson. We're squaring that to come up with a positive number. We then take the square root to undo the square. And n is the total number of counts. This will give you an error estimation to report in your project. This lesson has provided an overview of how a photometry project occurs from identification to the final measurement. In a generic sense, and it may need to be adapted to your tools and process. Software products mentioned are suggested only. You can use anything that you have available to you. Thank you for your time, and we look forward to seeing you in future brief video lessons.